Okay, so to begin understanding electrons, we are going to first talk about light. Light is a form of electromagnetic radiation, and so we're going to have a little physics lesson here. Electromagnetic radiation is composed of perpendicular oscillating waves. There's one for the electric field and one for the magnetic field. An electric field is a region where an electrically charged particle is going to experience a force. A magnetic field is a region where a magnetized particle is going to experience a force. All electromagnetic waves move through space at the same constant speed. It's called the speed of light. 3 times 10 to the 8th meters per second is really, really fast. 186,000 miles per second. So that's fast enough. It could circle the Earth 7 times in 1 second. Right? That's really fast. I always got a kick out of some of the old cartoons. Remember one in particular where this old guy, he blows out the candle and then he goes and he jumps into his bed before it gets dark from blowing out the candle. Is that possible? No, you can't move faster than the light. As soon as you extinguish the light, it's gone. And then that helps us to understand the mind-bogglingly largeness of the universe, because we are seeing light from stars that died millions of years ago. Because the light left them, they died, and the light is still traveling, and it's still getting to us. Yeah.
Is that why we see fireworks before we hear them?
Yes, exactly. It's why we see fireworks before we hear them. It's why we see lightning before we hear the thunder. Because light travels faster than sound. Yes?
Kind of going back to the star, so is that, you're saying that the light from the star, like they had died a long time ago, and light still traveled to us?
Right.
So is that the same for, like, I guess, constellations?
Yeah. It's a little hard to understand because on the scale of what we would see on Earth, there's no distance long enough that we could see that light was actually taking time to travel, right? Light just seems to hit us instantly, right? And so, but if you think about, say, a fountain, I've seen these fountains where they shoot some water, and you see the water come up, and it goes over and goes down, and it's doing this in pulses, right? And so you see this chunk of water go up and go down, and then another chunk of water, right? And so the water left the fountain, and the fountain stops putting out water, and the water keeps moving, and then the water hits over here later, right? So that's a little bit like the light coming from the stars. They sent out all this light, and then they stopped sending the light. But it takes time for the light to travel these ginormous distances. So we're living in the macroscopic world, and then we have the quantum world, which is mind-bogglingly small. You can study that. Or you can go the other way and study the mind-bogglingly large world of the entire universe, right? So you can go both directions. Personally, I like just the stuff I can see, right? But, thankfully we're all different, and some people really like messing around with the teeny, tiny stuff. And other people like dealing with astronomy and distances and things like that. So good thing we're all different. So here's an illustration of electromagnetic radiation. So there's an electric field component. These are sine waves. So this is going along. And then perpendicular to this is the magnetic field. And they're traveling in this direction. It's three-dimensional, but it's 2 planes that are perpendicular. Yeah. So this one's going up and down, and this one is perpendicular. The magnetic is perpendicular. So when lightning strikes, we see the light first, and then we hear the sound, because sound is not electromagnetic radiation. Sound travels at about 340 meters per second. Light travels at 3 times 10 to the 8th meters per second. Much, much faster. And so that's how you can, use the time difference between seeing the lightning and hearing the thunder to estimate how far is that lightning strike away from me. Right? So light is a wave, and waves have characteristics. So the amplitude, the height of a wave. So the wave goes along like this, and the height of the wave is the distance from this midpoint that it keeps crossing to the crest or the trough. That's how tall the wave is. Waves on water behave in much the same way, right? So if you think about going to the ocean and waves coming in, how tall is the wave? That's the amplitude. Then we also have the wavelength. The wavelength is the length of the wave. So from one crest to one crest, or from one trough to one trough. And that's given the symbol lambda. It's a Greek lowercase l. It looks like an upside down y, lambda. It's the distance between one crest and the next. So the wavelength of light determines the color that we perceive. So red light has a longer wavelength, yellow light is in the middle, and blue light has a shorter wavelength. The cells in our eyes get this signal and interpret it, and we view this as different colors. So the wavelength is the different colors of light. The amplitude, how tall the wave is how bright the light is. So a short amplitude is going to be a dim light. A large amplitude is going to be a bright or intense light. So you can have a very dim red light, or you can have a very intense red light, right? They have the same wavelength, it's just the amplitude is different.
The variation in color means?
Different wavelengths. It's a variation in color. Then we also have the frequency. And the frequency is the Greek letter nu, which looks disturbingly like a lowercase v. Sorry about that. Nu is straight and then a curve, as opposed to a v, which is two straight lines. Yeah, right? The frequency. So that's the number of waves that pass a point in a given period of time. Number of waves, also sometimes called the number of cycles. And so the unit for frequency is hertz, or cycles per second. And so 1 hertz is 1 cycle per second. So s to the minus 1 means 1 over second. So it's this many things per second. So if you're standing at the ocean and you're interested in the frequency of the waves coming in, you'd stand there and say, in the course of 5 minutes, count how many waves hit me, and divide by the time in seconds, and that will give you the frequency. So the total energy of the wave is proportional to the amplitude and to the frequency. If the amplitude is larger, you have more energy, and if the frequency is larger, you have more energy. And again, that makes sense if you think about standing in the surf. If you've got really big waves hitting you, you're going to notice that? Yeah, they might actually flatten you, right? Tall waves, lots of energy. Or if the waves are coming at you really, really fast, it's going to be more energy. Question?
You also write it as N frequency?
Frequency is not written as N, no.
It's in the PowerPoint, isn't it? Instead of B.
Here?
Yes, it says N.
I'll look into that.
No, wait, like it says like no.
L. Okay, so there's an issue with the font.
Okay.
Yeah, because nu is the Greek letter N, and so if the font gets messed up, it's going to show an N. Yeah. Yeah, I appreciate that. Thank you, and I'll look into that.
So V is frequency then? Lowercase V?
Lowercase v is velocity. Nu is frequency.
It's 'cause there's
This is nu. It's a Greek letter. And this is V. This is frequency, that's velocity. Yeah, that's smart, right?
It's pronounced what?
Nu. N-U. Nu. All those Greek letters. Because we ran out of English letters. You know, we used up so many of them that we've got to go to the Greek letters. So frequency is nu. This is a Greek letter. Yeah. Nu. And lambda. That's the Greek version of lowercase l. So this is lambda. And this one is nu. No, not NEW. Nu, the name of the Greek letter. Like alpha and beta and gamma and delta, epsilon, and all those guys. So for waves that are traveling at the same speed, a shorter wavelength means a higher frequency. A longer wavelength means a lower frequency because they're traveling at the same speed. All electromagnetic radiation travels at the speed of light. It's all going at the same speed. So we have this inverse relationship. So I'm going to draw you another crappy picture. So we can look at a wave like this or a wave like this. So the wavelength here is long, right? And the wavelength here is short. If I'm standing over here, or I'm standing down here, and this wave is traveling at the speed of light, and this wave is traveling at the speed of light, which one is going to hit me more frequently? The one on the bottom, right? Short wavelength, high frequency. So the frequency is equal to the speed divided by the wavelength. They're opposite. We're going to do some calculations with these equations, but what's more important is that you get the idea. And so if you can get these pictures, as ugly as they are, if you can keep the picture in your mind, we can figure most of it out. So color. The color of light is determined by the wavelength of the light, or by the frequency, because the frequency and the wavelength are related. They're inversely related. So here we have a picture of a prism. And if we take white light and pass it through the prism, as the light goes from one material into another, it is bent differently based on its wavelength. And then it comes through this other connection here between the glass and the air, and it gets bent again. And so we get the light gets separated by its wavelength, and we see a rainbow. So white light has all of the colors of visible light in it. It's called a spectrum. These are the colors, red, orange, yellow, green, blue, indigo, violet. And they always show up in the same order. So here in the rainbow we see there's red, orange, yellow, green, blue, indigo, and violet. So it's helpful to remember that order. So this is like some guy's weird name, Roy G. Biv. Red, orange, yellow, green, blue, indigo, violet. That's the order. This is why when children draw a rainbow, it often looks weird, because they know there's lots of colors, and so they put lots of colors in the rainbow, but they don't put them in the right order. And so you're like, I know you're drawing a rainbow, but something's funny about it. So, what is color? So here this woman's wearing a red shirt. Her shirt appears red because red light is reflected by her shirt, and other colors of light are absorbed by her shirt. And so the light that bounces off and comes to our eyes is the red light. And our brain sees red, literally, right? Her pants are blue. They appear blue because they are reflecting mostly blue light and absorbing other colors. Yes?
What happens if you're colorblind?
What happens if you're colorblind? That's an excellent question. So just a very superficial explanation. So you have rods and cones, and I forget which is which, but one of them, there's different kinds, and so you distinguish color.
Cones is for colors, rods is for shape.
Okay, cones is for color. CC, got it. So if you have a defect in your cones, then you may not be able to detect certain colors. Now, being colorblind doesn't mean that the world is black and white, and it doesn't mean that there are certain colors that are just like not there. Like if you can't see red, that somebody's red shirt just looks like there's nothing there. What happens is that your eye cannot distinguish between colors. Now, I know a little more about this than the average person because 4 of my 5 sons have some red-green color blindness. And so that's been kind of interesting. So one of them, went to the eye doctor, and they did this test where he's got these little circles, and one is green and one is red, and then in between there's all these different colors that are kind of mixed, So it gets into the middle, and you're like, what would you call that color? It's some sort of weird mauve color or something. These muddy colors that don't really have a name. And so the eye doctor said, put these, here's the green one, here's the red one, put them in order. And he could do the ones on the end, and the ones in the middle all looked the same to him. And his little brother, the one who isn't colorblind, said, can I do it? And he goes over and he just puts them in order. And James is like, what the heck? How did you do that? Well, he can see it, and James can't. So it showed up once. James was a rec leader for Vacation Bible School, and they were playing this game with the kids where they took brightly colored paper clips and threw them in the grass. And the kids had to pick up the paper clips. It's like you pick up the red ones and you pick up the blue ones and stuff. James could not see the red paper clips in the green grass. They were just like invisible. It would look like green grass-colored paper clips in the grass. They'd be hard to find, right? That's what it looked like to him. So it's really interesting. That's why we have some arguments about what color is that shirt. He thinks it's purple, and I say, no, it's navy blue. And it's because his interpretation of color is different. So, yeah, that's an excellent question. And interestingly, color blindness was originally called Daltonism because John Dalton was colorblind, and he was the one who first described it. So it's very interesting. Okay, wavelength of frequency. A laser dazzles the audience in a rock concert by emitting green light with a wavelength of 515 nanometers. Calculate the frequency. Like, okay, we were just talking about color, and that was kind of fun, and now you're throwing this at us. Well, we have that relationship. Frequency is equal to the speed of light divided by the wavelength. So the speed of light, and this would be given to you on an exam. I don't necessarily expect you to remember this. 3 times 10 to the 8th meters per second. And we want to divide that by the wavelength. The wavelength is 515 nanometers, we're told in the problem. Now, if I put that in here, 515 nanometers, is nanometers going to cancel with meters? No. So I need to convert that, and the easiest way to do that for this problem is to say, well, what does nano mean? It means times 10 to the minus 9. So that's 515 times 10 to the minus 9 meters. This is what nano means. So then the meters cancel out, and I'm going to end up with a unit of 1 over a second, which is the unit of frequency. So 3 times 10 to the 8th divided by 515 EE minus 9. 5.83 times 10 to the 14 per second. This is the frequency. Any questions? Yes, I can. So the calculations like this that we're going to see, the point of them is not converting units, but unit conversions do come into it because light is frequently measured in nanometers, and then we have, but the speed of light is in meters per second.
Are the units nanoseconds?
No, they are 1/second. Because the meter and the meter cancel out, and we're left with 1/second, which can also be written as 5.83 times 10 to the 14. Whoops, that's not a 4. Seconds to the -1. 5.83 times 10 to the 14 hertz. Those units are all the same. They just look different.
So on a test, would you want us to just leave it as 1/s, or would you want us to convert or put it in hertz?
That's a good question. What unit would you want on an exam? This would most likely be a multiple choice question, and I wouldn't be tricking you on the units, so just whatever the unit showed. It could be any one of these three. Yeah. And you just need to know that they're the same. This is on YouTube, and you can watch it on a loop over and over all day long. Okay, did that one. So we'll finish this section, and then we'll take a break. The electromagnetic spectrum. So visible light is only a small part of the electromagnetic spectrum. Shorter wavelengths, higher frequency light has higher energy. And so light that's more energetic than visible light is things like gamma rays and X-rays. And if we have lower energy, we have longer wavelengths, lower frequency, then we get into things like radio waves. Really high energy radiation can damage biological molecules. It can ionize molecules, turning them from molecules into ions, and then the ions have different chemical properties, and so then the cells don't function correctly anymore. So this is the electromagnetic spectrum, and this diagram is often misunderstood. So I want to point this out. So here we've got radio waves, microwaves, infrared. This is visible light. And we have ultraviolet, X-ray, and gamma rays. This little tiny section in here is very interesting to us because this is the electromagnetic radiation that we can see with our eyes. And so it's this little teeny tiny piece, but because it's so interesting to us, we're going to zoom in, and this part here, this is a zoomed in of this. Okay? So we've expanded it so we can see this is 750 nanometers up to 400 nanometers. This violet light does not correspond to gamma rays. Okay? Doesn't match up. This goes back over to here, right? And this red over here, this isn't radio waves. This red came from this little piece. Okay? So there's some questions on an experiment that people often give me like really crazy answers, and I can tell it's because they misunderstood this diagram. So there's a lot of information on here. There's a frequency line up here, so we're going from low frequency to high frequency. Here's the wavelength, so we're going from long wavelength to short wavelength because the wavelength and the frequency are inversely related. If one's large, the other is small. All of these things travel at the speed of light. They are light, they're just not visible, right? Radio waves, microwaves, gamma rays, X-rays, they're all the same thing, just different energies. So X-rays are just like really, really high energy light. It's just not visible. So read about microwaves, infrared, visible light, ultraviolet, and X-rays in the textbook. It's just little paragraphs, and you can read that. We really should be able to list radio, microwave, infrared, visible, ultraviolet, X-ray, and gamma rays in order. And you're like, oh, how do we learn how to do that? Well, Roy G. Biv. So we got Roy G. Biv. And over here, this is red. Next to red is infrared, or IR, infrared. And then the one before that is microwaves and gamma rays. And then on the other end, we've got violet, and what's next to violet? Ultraviolet, right? Like ultralord, UV light, ultraviolet. And then to the X-rays and the gamma rays. So then, something I always have to pause and think about is like, okay, which has higher energy, violet light or red light? Violet, because what gives me a sunburn? Ultraviolet light. This is higher in energy than visible light. It's high enough in energy that it can actually give you a burn, right?
So that's why the different colored suns are like dark blue or hotter?
Different colors of what?
Suns, because there's like blue, red, orange.
I think there is a relationship between the color and the temperature of something like a flame or a star, but I'm not sure exactly what it is. And then X-rays are higher in energy and gamma rays are the most high in energy. So a continuous spectrum, we get this continuous rainbow from red through violet. So here we've got white light passing through a prism. This has all the colors in it, and the prism separates them, and we see a beautiful rainbow. That's a picture of me and my daughter. She was a little younger then. We got to go to the NASA's Jet Propulsion Lab in Pasadena, and they have this cool infrared camera there. And so you see the camera showing, the video camera showing visible light, and then showing the infrared light. Infrared light is the radiation given off by a warm object. We can't see it with our eyes, but it can be detected. And so you've probably heard of like night vision goggles and stuff, and they're looking for criminals and they're using night vision, or the Army's using night vision. What the heck is that? Well, you can't see it with your eyes, but you can have essentially a digital camera that can detect infrared radiation. And the computer can process that and turn it into an image that we can see. And so that's this sort of image. And so you can see that our faces, my hands, apparently my phone, I've been taking a lot of pictures. It was probably pretty warm too. And then hair and our clothing is cooler, and then the stuff behind us is much cooler in temperature. And so you can get a picture of the temperatures of things. So in complete darkness, infrared imaging, you could see a person because of their heat signature, right? So it's kind of cool. High energy radiation, can be extremely damaging. It can kill you, but we can also use it to do good things like cure cancer. So one of the ways we use high energy radiation is a technique called gamma knife. So here we have radiation coming in to hit this tumor. Some tumors can't be operated on because the process of cutting you open to remove the tumor would do more damage than the tumor is already doing. You got a tumor in the middle of your brain. They're going to have to cut through your brain to get it out. That's just not going to work, right? So what do? Well, we can use radiation to kill the tumor. So here's a beam of radiation focused on the tumor. Now, the beam of radiation is going through healthy tissue, and it's going to do some damage to the healthy tissue. But we're not going to just send all of it in this one path. We're going to send some from this direction and from this direction. And so we're going to take multiple rays from lots of different directions. Each of those is going to do a small amount of damage to the healthy tissue. But because the tumor is getting all of them, the tumor is going to be really affected by the radiation. And most of medicine is about risk-benefit balance, right? So there's a risk to this procedure, but here's the possible benefit. And then so this, you've got some possibility for tissue damage, radiation sickness, etc. This can even cause future cancers. But if you don't use the technique, what's going to happen to the person? They're going to die, right? So we have a chance of helping them or maybe giving them a few more good years. So it's interesting how these different things can be used in very practical ways.